In this lecture, we will discuss mechanism of E1cB elimination, 13 examples of E1cB elimination, kinetics of E1cB elimination. We will see three flavors of E1cB. That is, E1cB, reversible, E1cB, irreversible, E1cB, anion. Then we will discuss evidences for E1cB mechanism and how do we determine E1cB versus E2. Before discussing the E1cB in detail, let us repeat what happens in E2 and E1 elimination, so that we understand the difference in E1cB. Consider this alkyl halide. X is a good leaving group, and with respect to it, this is beta hydrogen. One way of elimination is that base abstracts this beta proton, so that its bonding electrons are pushed in between alpha and beta carbon to eliminate the X. The product alkene is formed with side products, conjugate acid of base and the leaving group. In other words, we can say deprotonation and loss of leaving group is simultaneous. We have discussed such an elimination to be called as E2, because rate-determining step is bimolecular. Another way of elimination we discussed is that leaving group X leaves first to generate this carbocation intermediate. Base then abstracts the hydrogen from adjacent beta carbon to form this alkene product along with conjugate acid and leaving group. So in this case, loss of leaving group takes place first, which is then followed by deprotonation. We called such an elimination as E1 elimination, because first step is loss of leaving group and is slow and rate determining and involves only one molecule. There is another way of eliminating HX. That is, if the base abstracts this beta proton to generate a carbanion first, which then pushes the leaving group out, to form the alkene product, along with the conjugate acid and leaving group. Thus in this case, deprotonation occurs first, followed by loss of leaving group. Such an elimination is called E1cB. E1cB stands for elimination unimolecular conjugate base. Because this anion is the conjugate base of this acid, which loses a proton to a base. The second step, which is loss of poor leaving group from conjugate base, is slow and thus rate determining step. Therefore, it is also designated as unimolecular elimination E1 from a conjugate base, Cb. This lecture is based on E1cB. Consider this substrate having leaving group X, attached to carbon designated as alpha. The adjacent carbon is designated as beta, which has this hydrogen. So, in E1cB, this base abstracts beta hydrogen, to generate a carbanion, which then loses the leaving group, to generate alkene product. This abstraction of proton is fast and reversible, whereas, this expulsion of leaving group is slow, and hence rate determining. If we ponder over this reaction, the base will abstract the proton from this substrate, only if this is acidic enough. Thus this substrate is an acid, reacting with this base, to form this conjugate acid, and this conjugate base. The rate determining step involves only one molecule, which is conjugate base. Hence this reaction is classified as unimolecular elimination from conjugate base. Now what are the essential conditions for E1cB reaction? The first condition is a strong base is required. This is obvious because only a strong base can abstract the proton. Second condition is, very poor leaving group should be there. Because if the leaving group is strong, then it will be removed simultaneously with abstraction of proton via an E2 elimination. Examples of poor leaving groups are fluoride, chloride, hydroxide, phenoxide, orine sulfonate anion, etc. Third condition is, substrate should be acidic, that is, beta hydrogen with respect to leaving group of the substrate should be acidic. Otherwise formation of carbanion conjugate base intermediate is not possible. For beta hydrogen to be acidic, beta carbon should be attached with electron withdrawing group. Examples of electron withdrawing groups are phenyl, para-nitrophenyl, ortho-para-dinitrophenyl, unsaturated group like carbon-carbon double and triple bond, carbonyl group, or cyano group, etc. Let us understand E1cB elimination with some examples. Consider this substrate having a weak leaving group fluorine. This carbon is alpha and this is beta carbon, which is attached to electron withdrawing phenyl ring. This is treated with strong base sodium methoxide. So all the required conditions of E1cB reaction are satisfied. Thus, under such conditions, the first step will be fast reversible deprotonation of beta hydrogen, so that a stable carbanion is generated, because carbanion will be stabilized by electron withdrawing effect of phenyl as well as resonance stabilization into phenyl ring. This is the conjugate base of this acid. Second step will be expulsion of poor leaving group with the help of negative charge. This will be off-course slow and hence rate determining step. This will form this alkene which is called styrene. Consider this second example. The substrate is similar except that phenyl ring has electron withdrawing nitro groups at ortho and para position, which makes the phenyl ring overall more electron withdrawing, which in turn makes beta hydrogen more acidic than in the previous example. So the first step will be fast deprotonation of beta proton by strong amide base, to form this much stable carbanion conjugate base. This is followed by expulsion of weak leaving group fluoride anion. This is slow step and hence rate determining and leads to the formation of this alkene. Remember that the rate of this reaction will be faster than previous one, because phenyl ring in this case has two electron withdrawing nitro groups at ortho and para position which stabilize the carbanion conjugate base better than simple phenyl ring. Consider this third example. The substrate is called beta halocarbonyl compound. With respect to this leaving group X, this beta carbon has two hydrogens, and is attached to electron withdrawing carbonyl group. Upon treatment with strong base triethylamine, the first step is fast reversible deprotonation of beta hydrogen to form this carbanion conjugate base. This carbanion is in conjugation with carbonyl group. This is called enolate anion. Second step will be expulsion of leaving group like this, to form this alpha-beta unsaturated carbonyl compound. So the first step is the fast reversible deprotonation, followed by slow expulsion of the leaving group. This is rate determining step. Thus any carbonyl substrate like this, which has poor leaving group at beta position with respect to carbonyl group, will show E1cB elimination upon treatment with strong base. Consider this substrate. It is treated with aqueous acid and then with strong base triethylamine in diethyl ether solvent. This compound has ester and hydroxyl group. Therefore upon treatment with aqueous acid, lactonization will take place with expulsion of ethoxide group. This will form this lactone. Carefully examine the lactone structure. It has a carbonyl group, and with respect to it a leaving group chlorine at beta position and acidic methylene group occupies alpha position. Thus in the second step, amine base will abstract this acidic proton to form carbanion which will be resonance stabilized as enolate. This enolate then regains carbonyl group and expel the leaving group chlorine slowly. This is off-course rate determining step. Thus second reaction comprises of fast reversible deprotonation followed by slow expulsion of leaving group. This second reaction is E1cB elimination. In the last few examples, we have shown the deprotonation step as an equilibrium. But remember that these equilibria lie over to the left-hand side, because neither triethylamine nor hydroxide is basic enough to remove completely a proton next to a carbonyl group. But, because the loss of the leaving group is essentially irreversible, only a small amount of deprotonated carbonyl compound is necessary to keep the reaction going. The important point about substrates that undergo E1cB is that there is some form of anion stabilizing group next to the proton to be removed. It doesn't have to stabilize the anion very well, but, as long as it makes the proton more acidic, an E1cB mechanism has a chance. Consider this substrate with two phenyl rings helping to stabilize the anion and a carbamate anion as the leaving group. This proton has pKa of about 25 and can be deprotonated by secondary or tertiary amine as the base. The conjugate base formed has resonance-stabilized cyclopentadienyl anion. If we write this 5-membered ring here separately, we can see that removal of the proton by base forms a cyclopentadienyl anion which is having aromatic 6pi electrons. Likewise, this conjugate base formed is stable because it has cyclopentadienyl anion aromatic ring generated by loss of proton. This is followed by slow elimination of carbamate leaving group to give this product. Spontaneous loss of CO2 from this eliminated carbamate moiety gives amine. Another example is this beta-hydroxycarbonyl compound, which are the aldol addition products. These cyan blue hydrogens are adjacent to a carbonyl group, which makes these acidic. Thus, upon treatment with base potassium hydroxide, the cyan blue hydrogen is abstracted to form enolate anion. The enolate ion can push out this leaving group hydroxyl anion to form this alpha-beta unsaturated carbonyl compound as the product. If you pay attention, you will see this is the base-catalyzed dehydration step of aldol product. Consider this example. It is a case of deceptive substitution. It seems that mesyl group has substituted H of alcohol. But that is not the case. This is the structure of mesyl chloride. You see, this methyl group is directly attached to sulfonyl group, which is electron withdrawing in nature. Thus, these hydrogens are acidic enough to be deprotonated by a strong base triethylamine. This forms a conjugate base, which can then expel chloride anion to form this compound called sulfene. This sulfene then undergoes addition of alcohol on sulfur to form this methane sulfonate, also called mesylate. So this transformation is not a substitution reaction but involves an E1cB elimination followed by addition reaction. In this example, we can now directly say, based on our previous example, that this hydroxyl group, in the presence of base triethylamine and mesyl chloride, is transformed into mesylate group. This mesylate-bearing compound has an ester group which is electron withdrawing and makes these hydrogens acidic enough to be deprotonated by triethylamine base. Thus this step involves reversible deprotonation by amine base to form this carbanion, which is in conjugation with ester carbonyl. The enolate then forms ester back, and pushes out mesylate group to form this conjugated alkene. It is obvious that location of the double bond is defined by the position of acidic proton and the leaving group. Hydroxyl anion is never a leaving group in E2 reaction. But since it is first converted to a comparatively good leaving group mesylate, it seems that reaction can take E1 path because loss of mesylate leaving group will form a stable allylic carbocation. But in fact the mechanism is E1cB as shown. The most reliable way to spot a likely E1cB elimination is to see whether the product is a conjugated carbonyl group. If it is, the mechanism is probably E1cB. In this reaction, the product is formed in 90% yield with 2:1 mixture of E-Z alkene. E1cB reaction may be stereoselective. The above reaction, for example, gives mainly the E-alkene product, 2:1 with Z. The intermediate anion is planar, so the stereochemistry of the starting material is irrelevant, the less sterically hindered product is preferred, which is usually E-alkene. This substrate, for example, after double elimination gives only the E product. So it is stereoselective. In this example 10, the substrate is beta-hydroxycarbonyl. Upon treatment with mesyl chloride in the presence of pyridine base, the hydroxyl group will change into mesylate group, which is then eliminated via E1cB pathway to form alpha-beta conjugated carbonyl compound. In this reaction, the first step is the methylation at nitrogen to make it quaternary ammonium group. This hydrogen is positioned alpha to an electron withdrawing carbonyl group and can be abstracted by base hydroxide anion. The conjugate base is resonance stabilized in the form of enolate. The enolate, as seen in previous few examples, will push out nitrogen with 3 alkyl groups to position double bond here. Another example of the E1cB is in the formation of alkynes from alkanyl halides with NaNH2 in liquid ammonia. When alkanyl halides are treated with NaNH2 in NH3 as solvent, elimination to give the alkyne occurs. This reaction works even if the H and halogen are cis to each other, which would seem to rule out the E2 mechanism. Though the elimination when H and the halide are trans is much faster. NaNH2 is an extremely strong base. Being sp2 hybridized, the CH bond of the alkanyl halide is reasonably acidic, pKa about 40, and able to stabilize negative charge. Thus in this case, a two-step mechanism likely operates. The first step is fast deprotonation of alkanyl H to form a carbanion conjugate base intermediate which is relatively stable. This is then followed by slow loss of the leaving group to form alkyne product. A related situation to alkanyl halides where the E1cB mechanism can arise, is in the formation of benzene and other aroms. Although benzene does not have a true pi bond, many of the same principles of the E1cB still apply. Deprotonation of the aryl fluoride by the strong base, NaNH2, occurs first, giving a carbanion conjugate base. In this specific case, the second step is loss of the bad leaving group, fluorine, to form benzene. Now we will discuss kinetic rate equation of E1cB reaction. Consider that this beta-hydroxycarbonyl compound is treated with hydroxide base. Base reversibly abstracts the acidic proton to form this enolate. Let the equilibrium constant is K. The second step is slow and rate determining with rate constant K. Rate can be written as K times concentration of enolate. It seems that rate is first order as it depends on the concentration of one species enolate. But we know enolate is formed from substrate, by the abstraction of acidic proton by base. We can calculate the enolate concentration from equilibrium equation. Equilibrium constant K is equal to concentration of enolate times water concentration divided by substrate concentration times hydroxide concentration. From this we can write that enolate concentration is equal to equilibrium constant K divided by water concentration times substrate concentration times hydroxide concentration. We can substitute this value in rate equation. Rate equals rate constant K, and in place of enolate concentration, we can use the above equation. This rate constant K, equilibrium constant K and water concentration are all constant entities. So we write all three as constant, times substrate concentration, times hydroxide concentration. Thus, from this, it is clear that rate of E1cB reaction is dependent on substrate as well as hydroxide concentration. Thus, E1cB is unimolecular because rate determining step involves one molecule only, which is conjugate base. But the reaction shows second-order kinetics, because conjugate base is formed from substrate and base. We will now see that there are three flavors of E1cB elimination. The first one is E1cB reversible, abbreviated as E1cBr. It involves reversible fast deprotonation followed by slow elimination of leaving group. For example, take this substrate with leaving group X and a hydrogen on adjacent carbon, which must be attached to an electron withdrawing group, making the hydrogen acidic. The base abstracts this acidic hydrogen. This step is fast and reversible. This forms a carbanion conjugate base. The second step is slow and hence rate determining. The negative charge pushes out the leaving group X to form a double bond between the two carbons. The second type is E1cB irreversible, abbreviated as E1cB-IRR. It involves irreversible slow deprotonation, followed by fast elimination of leaving group. Consider this substrate having leaving group X, with an adjacent carbon bearing H, and the electron withdrawing group. The first step is irreversible slow deprotonation of acidic H by base to form a carbanion conjugate base. The second step is fast, in which negative charge kicks out the leaving group X, to form a double bond between the two carbons. The third type is E1cB anion. It involves irreversible fast deprotonation of H, followed by slow elimination of leaving group X. Consider this substrate with leaving group X, having hydrogen and electron withdrawing group attached to adjacent carbon. The first step is fast and involves deprotonation of acidic H by base, to form a carbanion conjugate base. The second step involves expulsion of leaving group X with the help of negative charge. This step is slow and forms a double bond between the two carbons. We will now discuss some evidences for E1cB mechanism and determine E1cB versus E2. The first is deuterium exchange. The first step of the E1cB reversible mechanism involves a reversible exchange of proton between the substrate and the base. In that case, if deuterium is present in the base, recovered starting material should contain deuterium. This was found to be the case in the following reaction. When this substrate was treated with deuterated sodium hydroxide base, the alkyne product was obtained after elimination of HCl. When the reaction was stopped before completion, there was deuterium in the recovered alkene. This recovered alkene with deuterium cannot be obtained if E2 mechanism was operating. Hence, it confirms the E1cB mechanism. Second evidence for E1cB comes from kinetic isotope effect. We have predicted that the E1cB mechanism would most likely be found with substrates containing acidic hydrogens and poor leaving groups. Compounds of this type, where Z is an electron withdrawing group, belong to this category because OPH is a very poor leaving group. In the presence of base, fast reversible deprotonation of acidic H to form carbanion conjugate base, followed by slow expulsion of leaving group with poor nucleofugalability, results in the formation of alkene. Some of the electron withdrawing groups include NO2, Me2S positive, ArSO2, Cn, COOR. OPH is a poor leaving group. Thus these are satisfying conditions for E1cB mechanism to operate. If we consider these two reaction with OPH leaving group and electron withdrawing groups attached to beta carbon, in the presence of NaOD base in D2O, the primary kinetic isotope effect of Kh by Kd was found to be 1. It means rate determining step doesn't involve bond breakage of substrate with H. This is compatible with an E1cB reversible mechanism, but not with an E2 mechanism, for which an isotope effect of perhaps 5 might be expected. OPH being extremely poor leaving group, hints that E1 is not possible. Thus, E1cB mechanism is confirmed. Third evidence is the effect of electron withdrawing group Z on the rate of elimination. Consider the same reaction as above. It was found that changes in the identity of Z had a dramatic effect on the relative rates of elimination. The rate of elimination with Z as NO2 was found to be 10 to the power 11 times faster than with Z as carboxylate. This is possible only if conjugate base is involved in the mechanism. This data also confirms the E1cB mechanism. Fourth evidence for E1cB mechanism comes from changing the leaving group. Consider this reaction, wherein base treatment gives alpha-beta unsaturated ketone product. This reaction shows a large primary kinetic isotope effect, meaning that CH is broken in the rate-determining step. This hints that it can be E2 elimination. If that is the case, we can do a confirmatory test. Changing the X in the para position of phenyl ring will have a large effect on the leaving group ability of OPH. And changing leaving group will change the rate of E2 reaction. Practically no rate change was observed on changing X, which rules out E2 mechanism. Both these observations hint for E1cB irreversible mechanism, which we have discussed earlier in this lecture, in which deprotonation is slow and rate determining, followed by elimination step, which is fast. Thus, the mechanism is E1cB irreversible, which explains the isotope effect observed, because in the first slow step, base abstracts the acidic proton to form the conjugate base. It also explains no rate change on changing the identity of the X, because breaking the CLG bond is not the rate-determining step in this case. Breaking the CLG bond is part of the rate-determining step in the E2. This rules out E2 and confirms E1cB irreversible mechanism. Another case is this reaction, wherein base treatment leads to elimination. The first observation in this reaction was that no primary kinetic isotope effect was seen. This rules out the E2 mechanism, because E2 mechanism shows significant isotope effect. The second observation was that there was strong influence of the identity of the leaving group on reaction rate. This rules out the possibility of E1cB irreversible. Thus, it means deprotonation is not rate determining, but breaking of CLG bond is rate determining, which is why leaving group identity influences the rate of elimination. Thus, the mechanism proposed for this reaction is as under. First step is fast irreversible deprotonation of acidic H by base to form a stable carbanion, which then slowly kicks out leaving group to form alkene. Another strong evidence for this mechanism is spectral detection of this carbanion. Thus, the mechanism of this elimination is called E1cB anion.